Hello. Okay, it's 6:30. Like we can start our second lecture. And first of all, like the first assignment is posted online this noon, and it's due 2 weeks from now. And it's a Jupyter notebook, and you will implement an multi-layer perceptron like all from scratch, like implementing the forward and backward paths. And some of the content will be introduced today, and also some requirement packages. You can also download here. If you have any questions, better to send emails to me or the TAs, and we can answer them quite quickly. And today we will introduce many about multi-layer perceptron and also how to do backpropagation. And today's agenda is divided by three parts. First is 50 minutes of multi-layer perceptrons and 10 minutes break. And we will introduce a very core part of the course called backpropagation. And then we go to the coding and tutorial to cover some of the basic concepts we introduced in the class and convert them into some coding problems. And for the first part, we will introduce the multi-layer perception. First is why those linear model we introduced last time was quite limited. And the second part is about the multi-layer perception. And the third part is the modern part, like why those multi-layer perception is still in use today. First of all, we want to do some recap for the linear model or linear classification model we introduced last time. Let's see, we have a simple linear model. It's just some linear map given some input. Given some input x, we do matrix multiplication plus bias, and followed by a certain kind of stepwise separation function that it's above 0, it's equal to 1, below 0 is equal to 0. And in the there he gives 3-dimensional examples that we classify some blue dots with some red dots. And the linear classifier is some hyperplane in the space that cut off the two class of examples. And it defines a linear boundary. But what if the data is not linear separable? And does it enough to solve every questions by these linear models? Of course, the answer is no. And we can see this simply by taking a look at an XOR logic function problem. And that's what brings down the whole deep learning in 30 years ago, that they find that this very simple linear model cannot solve all the problems. And the XOR is a very simple logic functions. If both of the inputs, if I have two inputs, x1 and x2, if both are the same, the output is equal to 0. If one of them, if they are different, the output is 1. That's quite a simple problem, but can we separate this example with a simple linear function? The plot will look like this. You can see that it seems like we cannot draw any of the linear lines to separate the red crossing plus sign, put all the green plus sign in one side of function, but the minus sign in another functions. So it's quite intuitive that this XOR function is not linear separable. And we want to prove this, why this XOR problem is not linear separable. Instead of doing those intuitive examples for those plots, we want to prove this. First, we will need to introduce some concepts. First is the concept of convex sets. A set X is convex if any line segment connecting 2 points in the set lies entirely within S. Like if we draw 2 samples within the sets, and we do a linear combination of the 2 points, it will draw a simple straight line across the two across the 2 points. If they're entirely within the sets, we call it convex sets. Here's another example that's not a convex set. If we have a croissant and we draw 2 points within the croissant, and if we take a linear combination of the 2 lines, very obviously, those points here are not within the sets. So this croissant is not a convex set. And let's prove the XOR problem is not simply linear separable. So linear classifier will divide the whole space into 2 half space. You can see that if we draw a simple linear functions, it will intuitively split the whole space into 2 subspace. For example, one subspace in green, another subspace in blue. And those two subspace is convex because any 2 points within each subspace, we connect them, they are still in the same subspace. So, but for the XOR problem, if we say that the positive samples are in the positive half space, and the line connecting them would always lie in the same subspace. For example, here, if those 2 points are in the same subspace, all the line connecting them will in the same subspace. And also the negative examples, if we connect them, if they are in the same subspace, that all points through the line will in the same subspace. But very obviously, we can see that there is one point in the crossing, in the intersects, that is both in one subset, in one subspace, and also in another half space. So this intersection lies in both half space. So we see that it's impossible because those half space is convex, but one point like lies in two subspace. It's impossible. So we prove this concept by finding an contradiction examples that was not covered by those convex sets concept. Here's another example. We see that the linear function cannot resolve all the problems we have. For example, the example I want to mention is that the linear function cannot solve those translation invariant problem. For example, if we're given an image of a cat, for example, or an image of a human, but sometimes it's still a human if I put it somewhere else. But as long as it lies in the image, we can see it's the same human. But for the linear classifier, we will prove that it's not possible for a linear classifier to have this property that when some of the patterns are translated or moved to another position, it still gives me the same output. For example, here we have two patterns, pattern A and pattern B. They are 16 dimension vectors, but the only difference is that pattern A, within the pattern A, the same pattern is translated. It moves right a little bit, moves right a little bit. But for pattern B also, it's translate a little bit, but they all belongs to the same family, two family, pattern A and pattern B. We want to have a linear classifier that take the sample thing, but will classify if it belongs to pattern A or pattern B. So for a linear classifier, we will use a fixed per pixel weights to weighted sum those pixels together and give an output. And we will see it's maybe above 0, we say it's positive, below 0, it's negative. The question is, can we find those weights that can separate those two family of samples? Because we need to shift the images and apply the same weights here, we want the output does not change. It means that to be invariant, so the y stay the same, all the weights of wi must be equal. Because like we say that we translate into one position, it still gives me the same answer. Translate to another position, it also gives me the same answer. All the weights must be equal to implement that. So if all the weights are equal, the model only counts the number of black pixels. But you can see that the two pattern has the same number of black pixels because black equals to 1, white equals to 0. So they have the same number of black pixels. So it is quite intuitive that the pattern A and pattern B are indistinguishable because they have same number of 1. So we'll recap a little bit. So in order to want this linear classifier to classify those translated examples, they have to have all weights to equal to the same value, but it results those same value restrict the model's performance that they cannot, they can only do this counting problem. So it's here we give another example that linear classifier cannot do another family of problem. They cannot achieve this translation invariant. So in order to overcome this kind of limitation of linear classifier, as we mentioned last time, we want to project this low dimensional space into some higher dimensional space such that those linear classifier works. For example, here we have x1 and x2, and we also introduce another feature, x1 times x2. And we can see that by introduce another new feature. Here, all first three samples all belong to 0, but the last one belongs to 1. And if we plot it in the three-dimensional space, if under 2 dimension only see the x1 or x2. Let me clean it a little bit. If only see from the 2-dimensional space, we will see that, okay, these 2 points belong to the first category, but the blue one belongs to another category. But we somehow lift up these points into 3 dimensions, that we add a third dimension that with a value of 1. So that there exists the hyperspace that can separate these 2 categories. For example, maybe I can draw a little bit to make it more intuitive. For example, if I visualize that into, I like a cube, like you can see that there is a linear classifier, a hyperplane that can cut these samples, that it divides the blue dots underneath the hyperplane, but the red dots above the hyperplane. So in this new space, the problem becomes linear separable. But one example is that if for all the problems, we need to design these new features by hand, it's quite hard. And also it's quite domain specific. For example, we have face images, it's with 10,000 dimensions. It's quite hard to design new dimensions that we can separate these faces. So the solution for neural network is that instead of designing those features by hand, we want to learn this non-linear high-dimensional mapping automatically, but we use the neural networks. It comes to our main topics. We want to have multi-layer perceptions, or MLPs. We can see MLP is a directed acyclic graph. Directed means that the connection has directions. It's point from one layer to another layer. Acyclic means there is no circle within the nets. For example, there's no certain kind of connection from previous layer to the next layer to form certain kind of circles. And some people also call this a feed-forward networks, because given some inputs, it gives to a next layer, also the next layer, and the even next layer. It's called feed-forward network. And its architecture, it's quite simple. We have an input layer that input X in, X input to the input layers, and you have some hidden layer that transform this input into some hidden states, some intermediate high-dimensional hidden states. And in the final output layer, it outputs some Y's that we want to do our objective functions or do the prediction. And in a formal term, here is one linear, one example, one layer of those multi-layer perceptions. For example, if we have a hidden vector coming from the previous layer, we still do a linear transformation to get the linear output Z. and we feed the linear output to a nonlinear activation functions, and it will give us certain kind of outputs. And this W is weight matrix, and the B is bias matrix. It's nothing different from the linear layer we introduced last time, but we're stacking multiple of layers. So why do we need to apply this non-linear function? As we mentioned, we want to learn certain kind of high-dimensional mapping. But what if we just take out all those activation function out and see we're stacking a lot of layers? Is there any different? So because for the linear multiplication, there's adjoint rows that two matrix multiplication can be put together and form to a single linear transformation. So no matter how many layers of linear function, it becomes another linear function. So no matter how deep a linear network it has no more any expressive power than a single layer linear model. So this kind of very simple activation of nonlinear functions breaks these linearities. It allows us to approximate more complex functions. Then we will introduce some very simple and basic common activation function. As we introduced last time, most old school activation function is this kind of S-shaped activation function. The sigmoid functions and the tanh functions. And the sigmoid function, its output is in the range of 0 and 1. You can interpret as the probability of some samples if those x equals 1 or not. But there's some problem with this kind of S-shaped activation function. First problem is that it has some vanish gradient function property. Is that because when the z goes too large or goes small, those gradient become very, very small, nearly 0. Even when within the center points, the gradient still is 2.5. So it's quite small as well. If we're stacking those gradients, multiple layers, and the sum of the gradient cannot pass to the previous layer. Also, the output is not zero-centered. It's always positive. So it has some properties for the neural network to learn. For the tanh function, it somehow normalizes these sigmoid functions. But you can see it still has some saturations. But because when the z value goes too large or too small, the gradient becomes 0. And also, it's within a bound, so that it cannot represent some very large or very small values. Another family of activation function is this kind of ReLU-shaped functions. So the ReLU is quite simple. Given some input z, it takes max value of 0 or the d. This kind of function is super efficient to implement because the operation is very simple. And it's a kind of produce some sparse activation because in current GPUs, the sparse activation actually saves your GPU memories. Also, there is no vanish gradient problem if it goes in the positive side of these functions. But you introduce new problem that if the value lies in the negative axis, the neuron will caught that because it's always 0, no gradient. A point lies here can never move to the positive axis. So that people are trying to find some smoother approximation of those ReLU functions. For example, the right-hand side, we have soft class functions. It's differentiable everywhere, but it's with those exponential functions, those computations are much more slower than those ReLU functions. And within those like 10 years, there are some new activation function. For example, those leaky ReLU functions. Instead of having all 0 in the negative axis, it introduced some very small slopes in the negative axis. Like it fixed the dead ReLU problem that if some points lies on the negative axis, it will gradually, you can the model still can learn from it. And it's commonly used in all of a generative adversarial network or deep multi-layer perceptrons. And within these 5 years, there's those GLU or switch functions. They're kind of those gating functions because they are trying to apply the input with some nonlinear functions. They find that it has very good property here. The difference between these two functions is in their like the nonlinear functions. This sigma s is simply the sigmoid functions we introduced above. Also, these 5 functions is what we call the commutative like it's like integration of the normal functions. For example, if you have a normal function, the CDF of this function means all the parts lies beyond lower than this value. For example, we have a value of x. The CDF of x means all the areas lies like smaller than the x values. So it has a very complicated form for this, but very intuitively, you can see it as the areas below the x value. So in this form, those very modern like GPT models, BERT model, VIT models, they try to use those GLU or switch function because they have some good properties that they have some very small value in the negative axis. Also, it's non-monotonic, means that it's not always increasing. It gives the model the chance to say that it will put some value and push them to the next negative axis or push them to the positive axis. But though for those ReLU functions or those monotonic leaky ReLU function, they have no property of this. So as we have introduced some of nonlinear functions, we want to see then how it solve our previous explained example of XOR problems. So we can actually design a simple network that can compute this XOR problem exactly. We use those hash threshold functions. Those hash threshold functions, it's a stepwise functions. They look like this. Like at the point of 0, it will become 1. At the point like smaller than 0, it will give us 0. So all the logic actions can be expressed as some function of those like step function or threshold function. For example, if I have 2 input x1 and x2, they are either 0 or 1. And the AND operation can be expressed in this way. X1 plus x2 minus 1.5, and they give it to these step functions. You can see if it's both 0, if one of the value is for AND operations, only if both are 1s, they will give us the 1. So only if 0, 1 and 0, 2 both are 1, it will give 0.5 within this bracket, and it will give us 1. Also, we can do the same for the OR logic. Like for OR logic, if one of them are 1, it will give us 1 for the outputs. It's still the same. If one of the x1 or x2 are 1, the output will be 1. And for the XOR logic, it's nothing but you have an AND, you can express an XOR logic in this form. It looks like an AND and with all with its positive values. So, maybe it's not so super clear. Let me rewrite this. So for the x, all functions, like it can looks like an AND of two values and opposite of all functions and with AND functions, so that we can see here it's another H2 is AND, H1 is all, and you can put them still in the formulations. It will give us the XOR functions. We can give an example of 1 and 1. We put in the first x1, it gives us n value of 1, 1. It gives us 1. And h2 is the all function of x1 and x2. It gives us 1 again. And for 1 and 1, the XOR function will give us 0. It gives us a correct answer. So no matter what the input is, this kind of circuits will always give us the value we want for the XOR function. So as we can see, those multi-layer perception can solve these XOR functions. We can see this multi-layer perception as in a new way. Like each layer compute a simple function, and stacking these layers gives us a composition of functions that in more general ways it can express in this. And each layer transforms the input a little bit and add more abstract representations. But in the end, the final layer produced the outcome based on those learned features. And if we view it in this kind of graphic form, in the end of the layer, the input is not linear separable, but gradually, it will become some function that can be separated by some very simple linear function in the very end layer. So in more complex form, those multi-layer perception can be seen as feature learning. For example, here's an image example. We also introduced showed this last time. With multiple layers stacked, the very lower layer, they detect some simple patterns like edges or lines. The mid layer combines these edges into parts. Higher layer assembles these parts into some more abstract objects like cats, dogs, or faces. And those output layers, as we mentioned last time, for regression tasks, we can use some linear function as the output and use the square laws to train the models. For the binary classification or the multi-class classifications, we can use those sigmoid function to output the probability of it's either 0 or 1, or use softmax function to output the probability if it belongs to one of the classes. So with this, more formally, how can this multi-layer perception feed our data? So in 30 years ago, there is a very important conclusion in neural networks. It's called universal approximation theory. I will read it. A feed-forward neural network with a single hidden layer that containing infinite number of neurons can approximate any continuous function on a complex set to arbitrary accuracy. It means that no matter how complicated this function is, as long as we have a simple multi-layer perception, a three-layer neural network, the input layer, a hidden layer, and an output layer. As long as this hidden layer is extraordinarily large, this neural network can approximate that function to arbitrary accuracy. And that's the theory. So it implies something that the neural network can be universal function approximators. So that nowadays people are trying to use these very simple ideas to approximate anything, our language, our images, or anything we can think of. all data, there are some functions, the function of input and output, and we use those neural network approximate them. And those neural network are universal function approximators. But one very tricky problem is that the theory only says that the network exists. The network exists, but it never say how to find those neural network or how large it need to be to approximate those functions. So different architecture gives us different form of this neural network and approximate functions. Also, we will, in the next session, we will see how to find those or how to optimize this network to approximate any functions. So the last part is that we want to see how the multi-layer perception exists in today's, like the era of large language models. There was a myth that like deep learning has replaced this multi-layer perception with other kind of architecture, because every day you can see on social media, there are thousands of new architecture posted online. They say that okay, this multi-layer perception is outdated, it's no more in use. But the real truth is that the multi-layer perception never left. They just changed the name, but it still exists in today's modern architectures, like transformers, the neural radiance fields. And in those transformers, the multi-layer perception is particularly very important. They consist of 2/3 of the total parameters or the computations. So every day you run your ChatGPT or DeepSeek, and most of the computation or the electricity is consumed by those multi-layer perception. Also, the neural radiance field, they use it to approximate those 3D data. The whole thing is represented by the multi-layer perception. For example, here's a typical architecture block within multi-layer perception. And those multi-layer perception is like the inner part of the sandwich of large language models. Sometimes they only talk about the self-attention layer, but they never talk about that those multiple layer perception that they are running on all tokens and that consume the majority of your compute nowadays. For example, the role one is that within those transformer or large language models, those multi-layer perception performs as the channel mixers. I will talk what the channel mixer is. If you know a little about those transformer architecture, you will know that the attention layer would mix the information between different tokens. For example, it have 2 words. For example, I eat. The 2 words they input to those transformer architectures, the attention layer will mix the information of different tokens, and they will combine their information and gives a new representation of the new vectors. And they look at different other words. But the channel mixer means that for the vector represent each of the words, it will mix the information within these vectors. For example, it has 10 dimensions, for example. It has 10 dimensions. The multi-layer perception will mix the information between the 10 dimensions. And we can see as a point-wise mixing for the information within each tokens. And typically it will look like this. For each token will expand its dimension into higher dimension. For example, 4 more times dimension as the inputs, and you will project down. Those are the architecture they will use it in modern transformer architectures. It's nothing but a 3-layer multi-layer perception, and it performs as a channel mixer. And there's another understanding of why this multi-layer perception performs in modern transformers. They say it is a kind of knowledge storage, or it's a kind of implicit memory within those transformers. They call it certain kind of key value memories. Like, for example, you have a large library. Every time you know certain kind of index, and you go into the library, you use the index to find the book here, and you will take the book out. And they say that those multi-layer perception will function as this kind of key value memory within those large models. They store the factual knowledge and the weights. For example, we see the multi-layer perception. You can see it's consists of two layers. One is the input, like certain kind of input layer in, go through this, and it gives us output. And they see this kind of input. Maybe I change the color a little bit. This input as a pattern detectors that each column, the input X acts as a query in, and each column of this matrix will perform as certain kind of pattern matcher, like a key values. They will match with the input as certain kind of detectors. If this column has lower cross product with the input, they will give us higher values. For example, if I give it a sentence of capital of France, when it sees the keyword of capital and France, it will give a certain kind of higher value in the middle, in the hidden vectors. For other values, it will give us 0 or a small value here. And for the decoders, each rows will place as some fact retrievals. So we have those indexed as 0 and 1 values, and we input that to the decoders, and it will retrieve the rows that corresponding to these. For example, this column is hit by this column, this rows for the encoders. It will give the direction of that vector out. And those decoder networks retrieve the stored vectors. For example, certain kind of vector belong to Paris, they will decode that out, so that they see this kind of as kind of key value memories for the transformer model. Because current the activation function is still certain kind of ReLU function or ReLU shape functions. They will only, most of the value are close to zeros. It gives us certain kind of very sparse activation in the middles. Only those values that hit by the encoders will be decoded. So you can see its performance quite similar to those key value pairs that gives us the direct or correct direction for the stored vector. The third row, now those multi-layer perception are used in those 3D vision or 3D computer vision very frequently. They use it not as the function to process the data. They can somehow use it to store the data itself. How they do this is they use it as certain kind of implicit neural representation. They use this multi-layer perception in a very special way. For example, I have a grid-like data, like images, that for each pixels, it has certain index for row or index for column. They put that index, the position information, into the multi-layer perception. For example, here, they put the index here into the multi-layer perception. It gives us the value of the pixel value at this point, and feed the data on feed the multi-layer perception on the data itself, so that no matter each predation I give it to this multi-layer perception, and it gives us the value for the data. So in the end of the day, we can replace an image of a 3D grid or a voxel or any kind of data that you can index into a multi-layer perception. It's certain kind of continuous function, because in the testing time, you can actually index not only the discrete value here, you can index the For example, in the training time, you only have 1, 2, 3, 4 for the index. But at the test time, you can index some 0.5, 0.5 into the network, and it can give you the value at the point does not exist in the original data. So we call it some kind of continuous function. So this multi-layer perceptron F act as the certain kind of coordinate-wise look at tables. So it uses the index for the original data as a key and input to the multi-layer perception. The output is the value. And then the network weights theta acts as they compress the whole data. Then they can use that to compress a lot of new things. Like, so now everything on our planet, the pixels, the audios, the 3D things, everything can be compressed into a single neural network. And they call it implicit because they do not explicit or directly compress data somehow. They use a lookup table to store the data itself. Say they call it implicit neural representations. So the last row I would like to mention is about the mixture of experts. Like today, as the model gets larger and larger, those multi-layer perception get also wider and wider. Like this dense multi-layer perception become quite expensive because we know that it consumes like 2/3 of the total computation of those large models. And this solution is mixture of expert. The name is quite complicated. What does mixture of expert means? It actually means something like this. Like for a multi-layer perception, we still put it in this way. And it will be good if some of the value here are somehow 0, so that we can directly not compute its matrix multiplication in the decoder. For example, we somehow have 4 groups of activations. And here. And if only the red group has non-zero value, for the other 3 groups, they'll have all 0 values. So it's quite simple that we do not do the matrix multiplication in the outputs, and we save the computations. And it gives us certain kind of sparse computation because most of the computation are not used. Those columns, they are not computed. So also, because the output does not compute it, even if the input matrix, they cannot be still be ignored. Only this small part of computation can be computed because it's you can see as like point-wise computations. You just remove some columns and value for those multi-layer perceptions. So if we want to implement it in a more like direct ways, we can divide those one giant multi-layer perception into multiple smaller multi-layer perception, or we all call it expert. And we have some router networks to select which expert we want to activate. And we only activate, for example, the top 2 activate. Those router will give a score for each of the expert. For example, they give higher score for expert 2 and expert 4. So we choose them. And it's somehow you can use it as use large language model. They use it as per token. Like for each token, they will select some smaller experts for computations. Also, you can use it for per sentence selections or for different granularities. And this gives us the freedom that, okay, we do not activate all things. We just activate some of the parameters or computations. And in the runtime, it's very cheap to run. So that's why those Mixtra or DeepSeek was quite good or use very large model, but it used much lower inference cost because they only activate only small fraction of the compute of the large models. So a little bit summary of the first part is that we show those linear models, they are quite limited. As a lot of problems cannot be solved. Those multi-layer perception are introduced to add some non-linearity to these functions, and then they will allow universal approximation. And those deeper multi-layer perception will perform as feature learning. They learn the feature in hierarchical ways, that different layer in different features. And some modern usage of multi-layer perceptions, also in transformers, in neural radiance field, and so on and so forth. So the next step is we want to introduce backpropagations. So why we want to do this backpropagation? Because the universal approximation theory we introduced above just guarantee we have a good weights here. But how do we find those weights? It's another problem. That, for example, everybody has the potential to be Bill Gates, but how can you yourself become a billionaire? That's the question of you. So we will treat the training of neural network as an optimization problem. We will define some loss function. It will measure how good or bad the output is. And we will minimize the whole loss functions with respect to our parameters. And we will take gradient descent to update the weights. And to do this, for neural network, it's still a little bit different than the simple gradient descent we introduced last time. The backpropagation add on some techniques to make the simple idea scale to large, deeper network. And okay, that's the end of the first sections, and we will introduce backpropagation in the next part. So we may have 10 seconds for you to take a break. Right, 10 seconds.过完年的了。
应该其中的比重挺大的，如果过年大家都才好。
我可以考虑把它再往后，就所有人往后推一走。我想一下吧，我想一下，因为你我尽快吧，我觉得这个还是有道理的，反正往后可以往后推一走的。我想一下，然后这周之内吧。OK，好。
那您大概就是在提上哪个方面？
就是那个 learn，或者是给大家发邮件吧，就是
这样。还有一个说我们期中和期末都是一样。
都一样，因为这个开卷太简单，就是就是因为会有一点点，其实很简单，今天对。
那coding 可以。
coding 不太比较少。And also we have a Slido. If you have any question, you can scan the QR code to put it here. I will answer it later, if that's more convenient for you.
没有很懂这一块。
就是这个其实，
就它这个梯度是负的嘛？
对。 Hello, hello. So here's we have one question here, like how can MLP function as a channel mixer? Okay, it's quite intuitive. Like the input is vector, like and channel means like different dimension are called I call this kind of channels. For example, I have like 16 dimensions, and we have a multi-layer perceptions like goes on it. And it somehow mixes information of different dimensions. For example, at each hidden partition, you actually take a weighted sum of the 16 dimensions here. You add nonlinear functions, and you also add have a mixing of this hidden vector. I don't know how much it is. It's a d dimension. For example, not d. 16 dimensions, and you mix them together here. And then you mix also the hidden values again here. So every element in the output is a certain kind of weighted sum and mixing of the information for those input values. So they call it channel mixers. So each dimension, they call it certain kind of channel. And different from the token mixer is that it does not exchange information between different tokens. Like in language models, like every word is mapped to a vector. And this channel mixer only exchange information within one word of one vector. They do not exchange information between different words. That's what they call it, a channel mixer. Okay, let's go to the second part. So in the second part, we will basically introduce backpropagation. That I will say the most important concepts that we should learn in a deep learning class, because that's what it for. Like Jerry Hinton, like he will say that he won the Nobel Prize by reinventing like the backpropagation. First, we'll go through the problem definition and then why this backpropagation is needed. Then we go to the modern part of backpropagation, how it's still in use nowadays. And in the last part is some application and conclusion. First, like the deep learning is all in all, it's an optimization game. Like we input some data into the network, it goes through layers of parameters, and in the output, it has some output. And we have a ground truth or certain kind of supervision in the very end. We want to optimize this objective or loss functions, and by updating the parameters here. And we can write it as a simple optimization problem. So last time we already mentioned this. We optimized this large neural network by taking this gradient descent. And if what is great, how can we see this gradient descent is we can see it in the loss landscape. Like we have different parameters as certain kind of axis, and the z-axis we will see it as the value of these objective functions. And in the end of the day, we're going through certain kind of direction such that it minimizes the overall objective. And we would like to find the lowest point on this loss landscape. And the gradient descent is this kind of process. Like we have current parameter theta t, and we would like to update our parameter a little bit. Then the update rule is we go along the direction of the gradient of the loss with respect to our parameters. And the eta is the learning rate or a step size. And it's like just we are going downhill the mountains. Every time we just go one step, and gradually we will go to the bottom of the hill. And the core challenge here is how will we compute this gradient for those very deep, very large neural networks? So a very simple idea is that we do a numerical differentiation. That's the definition of this gradient. And why do we do not use this simplistic method, but reinvent a new kind of method called backpropagation? And by definition, we need to add a little bit step size on one of the parameters, and we run two forward pass of the models and get the objective, and the changes of the losses, we will get the changes and divide it by those small variations. And that's the definition of a gradient. So why that's not happening right now? Because that will give us a computational disasters. Like if I would like to compute the gradient for each of the parameters, we will need to run two simple forward paths, one with this variation, one without. So if we have a modern large language model with 100 billion of parameters, we need to run like 2 times 100 billion forward paths to have one single update step of all the parameters. That is super slow, and it's some compute we cannot afford. And this kind of method is only used when we want to do the gradient checking that these parameters has the correct parameters or do the correct perform of those backpropagation or to do debugging. And another thing is that those neural network, when they stack in multiple layers, we can see them as a chain of a nested function or composite function, we call it. And the chain rule of the derivative, like you have to have learned in your old calculus classes. If we want to find a derivative of one function with respect to some functions followed by multiple steps, we will apply those chain rules. For example, the x is input by h, and the h output is input by g. The g output is input to f. And if we want to do the gradient of the final output to the very beginning of the functions, we will need to first compute the gradient with respect to some intermediate variables and compute and times the intermediate variable gradient with respect to the first ones. So here we can decompose a large gradient chain rule of gradient descent into multiple components. Like first, the final output to some intermediate outputs, and those intermediate outputs to another intermediate output before it, and again do that. So it somehow decomposes a large problem into some smaller problems. So a gradient to the current layers or current variables can be computed by decompose it into some upper stream like informations here and some local information here. Like we somehow decompose a large problem into some smaller problem. It measures like how my output changes in terms of the final output changes. My current layer output, the U changes in terms of the final output changes, and how much my input changes to my current output changes. So the magic of backpropagation is that it's a kind of anesthetic differentiations. Like we will use the chain rule to compute the gradient of all parameters simultaneously. It's not computed one by one. It's simultaneously all gradients computed at once. Also, the computational complexity, if we count the number of calls for a forward pass, the complexity of compute a backward pass is exactly the same, or like not exactly the same. It's at the same magnitude of the complexity of the input forward. And instead of doing multiple forward pass, we're just doing one backward pass. So that's the magic of backpropagation. It do a lot of things, and you see that it's the driving force of modern deep learning. So if backpropagation is so fast, but is there any problem here? Like the backpropagation is super fast, but it's still very computational intensive. Like if you are now running the like PyTorch code, if you're only doing the forward, like you use the model dot eval or torch with no gradient, it will put the model into forward mode only. Like at every layer, you only compute the output for the current layer, and you throw all previous layers gradient or activation back, and the memory is quite low. But if you want to train a model, you need the backpropagations, because when you want to compute the gradient for the current layer, you need the gradient from the next layer and all the intermediate activation. You must save them all together. You need to cache all the intermediate activation in your RAM. I will mention that later, why this is so important. And that becomes better because you want to save all the gradient from future layers, all the activations here. So it becomes a very important problem, so that those training of large models compute a lot of GPU memories compared to just doing inference. So we'll go down to what the real backpropagation is and why it needs some tricks. So we will give some formulation of how this backpropagation is. In the previous multi-layer perception, we call it a directed acyclic graph. Here is again, like different layer of those models can be chained together as a directed acyclic graph. Like now the unit is not a neuron, it's a layer. And the graph of function transformations, they chain by certain kind of input. Each of those connections, you can see it as input and output of a layer, and we pass on to the next layers, and altogether it forms a certain kind of multi-layer acyclic graph. Like for the simplest multi-layer perception, you can just think of it as a very simple line graph and one layer input to another. But in the real case, the graph can be much more complicated for modern architectures. So consider the simplest case. We have a chain. Like the model has L layers, and the L layer, small l, has a vector weight of theta L. And when we're doing the forward pass, like the output of previous layer or the input of my current layer is input to the current function, and it has some parameters, and it altogether gives some outputs. And an example of such computation is what we call MLP, like we just mentioned now. And in the end of the story, we will compute certain kind of loss functions for the output with ground truth y. Overall, we want to sum up all the loss function of all training samples. For each training sample, there has a small singular loss function, and we sum them together. We want to minimize this objective function with respect to all the thetas. So we do the gradient descent. We compute the gradient with respect to all the model parameters here. And by design, each layer will be differentiable with respect to the inputs and also the parameters. So we will take the last objective functions gradient with respect to all the parameters, and we take downhill this direction and go downhill. And the very hard way is that we can see this kind of objective function as a nested function of all the parameters and the inputs, and it become a massive nested functions. And every time we want to evaluate one particular layers, we will take the full partial derivative from the end of the layer back to that layer. But we have a better tricks to compute that, because this kind of computation, when we compute one layers, it need for recompute all the information above, but back propagation saves all the computation here. So we want to review a little bit the matrix calculus. Like the x is a vector of n times 1. We define the function as the function of those vectors. And if y is a scalar, the derivative is a row vector in this form. And if y is a vector, the output is a vector, its gradient with respect to the x is a Jacobian matrix, such that each of those elements of this Jacobian functions, a matrix, is equal to the gradient of the ith value gradient with respect to the j's input. And the derivative is in the form of size of m times n. So if y is a scalar and x is a matrix, we also have another matrix to denote like just concatenations of all those vectorized gradient, and it gives a matrix of m by n. And the chain rules in the matrix form looks like this, and the derivative, if we want to compute the gradient of the edge with respect to the input x, we will first compute the gradient with respect to f with respect to g, and times the gradient of g with respect to x. And altogether, it will look like this: one component times another component. And in the matrix form, you will give us a matrix of n by n. It's a multiplications of matrix multiplication of a matrix of m by p times p by n. So it's not super different from what we talked about for the scalar case, but it's in the matrix form. So when we want to compute the gradient for parameters, we have a final loss. We take respect to one of the parameters, like this kind of gradient measures how much the output changes if my parameter theta I changes a little bit. So we do a certain kind of recursive computations to compute for example, we'll take the last layer, for example. If we want to compute the parameters update for the last layer, we use the chain rule to compute the gradient with respect to my output xl, and the gradient of xl with respect to theta l. And it's this kind of gradient measures how much the losses changes when the parameter changes a little bit. So it's a product of this function, and this function. If I look one layer before, we can see that we compute one more layers, and we have the loss function with respect to the last layer, the last layer output with respect to the last layer input, and the last layer input with respect to the theta l minus 1. If we write that down all recursively, we can see a very interesting pattern is that most of the computation are actually shared. All the blue terms are shared. So if we want to compute one layer, most of the compute has already been computed in the next layers, and most of computation, we can borrow it back to do the computation now for these layers. And the new computation I need to do is this. So all the blue terms are shared. And we can share such that kind of computations, use these notations to do all the back propagations. So the core idea of back propagation is that we reuse those computation we have found within this chain rules. We have the gradient from the next layer that's already computed in the next layer, and we borrow it back to our current layer and only do the local gradient computation at each layers. This allows to reuse the gradient, compute from the future layers to find the gradient of current layers. So it gives us a very efficient backward pass. Like instead of when doing the current layer gradient computation, instead of doing all the computations, we only need to do the local computation and times the shared computations we already computed in the next layers. And we will iteratively do this from the last layer to the first layer. And if you have learned certain kind of classical algorithm class, this will call it dynamic programming. We will see why this is called dynamic programming. So what is called a dynamic programming? So if you have taken some algorithm classes, or you have taken some undergrads in computer science, you will know that dynamic programming is the most interesting or like the hardest part in those algorithm classes because it has certain kind of recursive pattern. For example, here is a very classical dynamic programming problem that we have a starting point, we have an end point. If we ask how many different passes we can go from the starting point to the end point. And this kind of problem has certain kind of recursive form. For example, if I want to solve the, we have like 4 rows, 5 columns. We want to solve those 4 or 5 problems. It has to go from one of the 3 positions here. The 3 rows, the 5 columns, plus the 3 rows, 4 columns, plus the 3 rows, 4 rows, 4 columns. So if I want to go to these cells, I must to either go from this cell, or this cell. So each of the larger problems can be decomposed into some smaller problem. And those structure of sub-problems, instead of compute them all together, we can solve them individually. Like we can first solve this smaller problem. And this larger problem can and store the value here, and we can sum up them all together. And this kind of problem that we can decompose a large problem into some local sub structures is called the dynamic programming. And we can store the intermediate results, smaller problem, the results, and to save the computation for the large problem. So the idea of backpropagation is that we can see the computation of the gradient as a larger problem, and we can decompose the larger problem by breaking it up into some smaller problems, such that solving those smaller problems like naturally leads to our optimization of the larger problem. Also, we want to save the results, like memorize the intermediate results. So you can see the backpropagation as certain kind of a trade time, memory for time. So in backpropagations, the sub-problem is that the gradient of the future layers. If I compute the gradient of the future layers, we can then compute the gradient of the current layer. You compute it once, you store it, you pass it back to the previous layer. For example, here, if I want to compute the gradient of H, and we store the gradient with respect to the next layers, the gradient of Y, and future layers gradient are computed and can be reused. And we only compute the local gradient of the current layers. And instead of computing all from scratch again, with the complexity of n times n squared. N is the number of layers. Here we use the idea of dynamic programming. Like we save all the results for future layers, and we only need the computation of O(n). And here is a diagram for how this computation is saved or reused. Like for each layers, we will have the input vectors and the weights as input, and it all go through the end of the layers, and it will back propagate through one of the parameters. For example, the objective with respect to θ2, or the objective, the gradient of objective with respect to the θ1. And we can see that most of computation are shared. Like, or if we already go to θ2, we can actually save a lot of this computation and just reuse it for the computation of θ1. So at each, we can see it in a more micro perspective. At each layer, the goal is to update the parameters. And in the forward pass, the previous layer outputs go to me, and I pass it to someone else. And in the backward pass, someone passes the gradient with respect to my outputs, and I pass back the gradient back to my inputs. And I would not need to output the gradient with respect to my current weights. So during training, each layer has 3 inputs. Like in the forward pass has the input activation and my parameters, and for the backward pass, it has my gradient with respect to my output and also my parameters. Also, it has 3 outputs. One output is in the forward pass. I give out my output for my like forward computation, and backward pass, my outputs is the gradient with respect to my inputs. Also, we have the gradient with respect to my current layer parameters. So for each layer, we need to evaluate the 3 values: my output features, the gradient with respect to my inputs, and the gradient with respect to my weights. So if I do it for all layers, you can see that in the forward pass, we do 1 layer forward computations, and in backward pass, we compute the loss derivative iteratively, top to down, to bottom, and most of the computation are already be computed. And at each layer, only this part need to be recomputed. Also, we will update the parameters. This part, the gradient with respect to my output is already computed. Also, we need to compute this gradient with respect to my own weights and doing 1-step parameter updates. We will take some example of those in linear layer or multi-layer perception. For example, for the linear layer, we will first compute the gradient with respect to my inputs. A linear layer is nothing but a matrix multiplication with respect by input. And we take the back propagation to the input. We receive the gradient from my outputs. We will call it G out. We want to compute the input, the gradient with respect to my inputs, and pass it to the previous layer. We call it G in. And we reuse the chain rules because the linear, the G out is given, and the gradient with respect to input as theta of Wx in gradient of this with respect to this, and it's nothing but the weight matrix. And the resulting gradient rule is super simple, that we have another form of feed-forward pass or backward pass is look exactly the same as a forward pass. The only difference is that it is the output gradient times my weights. You can see a certain kind of symmetry here. And the forward with our input times the matrix. And the backward, it's output gradient times the weight matrix. It gives us the input matrix, input gradient. Also, another thing is that we want to propagate to the weight so that we can update the weight. So the goal is to compute the gradient with respect to the weights. So we already have the G out. So we'll apply the chain rule again. The first part is already computed, and the second part is that we have the output, the linear output gradient with respect to my weights. So the weights is nothing but our gradient, output gradient times the input feature vector. But you have to match the dimension so that it gives you the correct shape of the gradient. Then we use those computed gradients to update the weights with the gradient weight update rule. So we can see as certain kind of diagram form. Input in, we have linear multiplications, a ReLU function, another layer of linear multiplications, and we have output, and it gives a loss function, maybe a L2 loss function, and you will need to backpropagate this all to above. And in the backpropagation time, because the L2 function, its gradient is nothing but we take the 2 in front 2 times, like y hat minus y. And this is what it gives. And the gradient with respect to this layer's output. And again, it times the weights to give the gradient with respect to these layers input. And again, it matrix it back because the ReLU function we have seen it. It's nothing but if the input value is positive, all the gradient at 1. If the input value are negative, all the gradient 0. It's certain kind of masking times the matrix, the gradient of the output. And again, it goes to the G3. And the G3 times the W1, it gives the gradient with respect to the G4. And then we can see a global view. We do the forward pass, and also we can then do a symmetric backward pass. You can see it's exactly symmetric. Exactly symmetric. So the forward pass is nothing but the weight times the inputs. And the backward pass is another weight times the gradient. Also, by updating the weight itself, it's nothing but the gradient, the gradient times the input activation functions. So we roll out the full computational graph. We can see that 2 things. The forward pass and backward pass, they're symmetric. The second thing is that they consume almost the same, because some of the matrix multiplication, they have the different shapes. So they have a little variation in the computation, but the backward complexity is almost the same as the input, the forward pass. In terms of more complicated graph of the organization of the graph, for example, where some of the more complicated neural network, such as a residual network or those concatenations, it may branch out the activation into different parts and feed to different sub-branch of the network. Or it has certain kind of merging operation that merges out to feature vectors and input to next layers. When they do this kind of branching or merging, it's do certain kind of parameter sharing, because that or for one layer, it somehow applies to different inputs or outputs. You can see a certain kind of parameter sharing, or later this parameter sharing will be seen everywhere. And in this form, the gradient with respect to those shared parameters will be summed for the branches that it branches out, sum them together. So in this more graphical form or more abstract form, this backpropagation can let us optimize any node or edges on this graph. Like this node is the function or the weights. The edges is a variable or the input and output features in those computational graph. Like to any scalar outputs, like the scalar cost, you can do those gradient with respect to any of the node or edges. And because of the backpropagation, most of the computation are saved. When you compute how the loss changes when the weights changes, it will looks like this. Also, we can also take the gradient of the output objective function with respect some of the inputs. It will denote how much the cost changes when the input data itself changes. And even we take those abstract view of those backpropagations, we'll see that there is a huge problem here is that they will show some certain kind of vanishing gradients. For example, we call the chain rules, it's the gradient of all previous layer times every the gradients of every layer's output with respect to its input. If we consider a sigmoid function like in this form, like it last we just explained, well, looks like this one. It's S-shaped function. Its derivative is like this. Its maximum value is 0.5. So the problem is that if the gradient is some gradient of the last layer and times 0.5, 0.5, 0.5, that even is the maximum value. The gradient with respect to first layers or the first few layers, it will gradually go down to 0 quite quickly. The signal of the gradient will die out very quickly when it reaches the earlier layer. So that's the point. We will introduce a lot of techniques to preserve the magnitude of the gradients. And later, in the next lecture, using the residual connection or with other kind of activation function. And here, I want to pause a little bit. We will do a small quiz. Small quiz of 3 very simple problems. So everyone can scan the QR code, and we will have 3 questions, quiz problem here. We'll go through. Then the first page is that you will need to put down a name or nickname or a username of yourself, and that then will go on to start the pool. Okay, start it. Okay, you can now like put your name here. Maybe we'll wait until like maybe there was 30 people join this session. I'll go on to the first question. Okay. 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 I think that's it. And we'll move on to maybe the first question. Maybe a few seconds. I think someone's still joining. Okay. No. Okay. Okay. We may go to the first question. You have 30 seconds. If we stack 100 full conducting layer without any activation function, what is the mathematical equivalent of this deep networks? A very deep nonlinear classifier, B, a random forest, C, a single linear transformation, D, it depends on the initializations. Oh, no. Okay. I think most of you knows that. Okay, the correct answer is that okay, we in the end of the day, it shrinks to a single linear transformation because those linear functions are the two linear matrix multiply together. They can absorb together into a single linear transformations. Okay, each question only have 30 seconds, so you have to like take your time. We go to the second question. Second question is that when vanishing gradient problem occurs in very deep networks, like which part of the network suffer the most? First is the output layer. The B is the input or the early layers. C is the mid layers. The fourth is all layers suffer equally due to the chain rule coupling. I think. Okay. I see that there are most of you select the answer B. And even some of you say that's in the mid layer because they are furthest from both the data points and the loss. I think the correct answer is B, because as we mentioned earlier, that the gradient is multicolous, like when more gradient are applied more, it shrinks to smaller magnitude, and it's get for the early and input layers, there are more terms to multiply together, so the gradient value becomes smaller. And now we move on to the third question. In certain kind of network, value goes into two branches. How its gradient it's calculated during backpropagation. By averaging, by multiplying, by taking larger gradients, or by taking the sum of both branches. And maybe I need to, okay, 30 or 30 people. So I think that's just one light away. Like I just mentioned, like by branching the activation function into multiple branches, it's actually a form of parameter sharing, that the same parameters are branched out, like reused multiple times. So this kind of gradient, it's certain kind of summation of multiple gradients back from to this layer. So the correct answer is D. So okay, so that's a small quiz. So we go back to our like lecture. Then I want to talk a little bit about modern backpropagations. So those things I just introduced above is something like every deep learning class will introduce, but this part is not. Because there is a gap between theory and reality. Like in the textbook, in the backpropagation, we'll have infinite number of memories. And also in computer, we actually we'll assume we'll have infinite precision. Like each number can be reproduced by very long 0, 1 bits. And the the backward function will handle everything. But in the real world, like the GPU is very expensive. And sometimes even one model, one batch size of one can fill up the whole GPU. And also sometimes we need to low precision training to do the backpropagations and low precisions. And also there's a risk of like the memory go out the GPU memories. So here are a lot of challenges that modern model are trained using those backpropagations. And one important problem we want to solve, discuss right now is that if we only have limited GPU memories, how do those backpropagation works, or how to modify them to make them work? So the memory bottleneck, we will see why those backpropagation needs so many GPU memories. Of course, when we store a model in the GPUs, we need to save one copy of the weights. Here, we need to save the one copy of the weights. Also, we need to save one copy of the optimizer or the gradients of the weights as well to do the model updates. But the killer is that the problem is that instead of saving the weights and the parameters, a lot of the memory are consumed by saving the intermediate activations. Because as we just mentioned, like to do this backpropagation, we need to save the intermediate activations and to compute it to pass it to the previous layer to do the backpropagation. And the standard backpropagation need to save all intermediate activations to calculate the gradients. And somehow we are trading the time for memory, so that we use more memory to store the intermediate activations, but we use less time to do computations. But when modern GPU are limited, they cannot store all the activation. There might be some problem, or we can do something in between. If we do not store all the activation, or do we recompute all things. This technique is called gradient checkpointing, but we somehow trade back a little bit. We trade compute for memory again. We do not save everything. We only save some intermediate features and the layers. But when doing the backpropagations, we recompute the forward passes to get the activation for some nearby activations, and we do the gradient computations. So the idea is quite simple, and like in storage, we only store part of the activations, but in the backward pass, we either we do another pass of some forward passes to get those intermediate results, but we do not store them. We only use them in the backpropagation computations. So the memory somehow reduces from OL to squared L because we only need to store parts of the memories, but you will spend some speed to do the extra feed forward passes again. So it's slower, but uses less memory. So if you are doing some training that requires large memory, but you only have a small memory, but it runs decently fast, that's the technique you can use. Another technique is every day people are using those mixed precision training. So in GPU, the weights need to represent by some format of 0 and bits. For example, the FP32 is the common format to store the weights, but it's a high precision. But sometimes we want to do fast computation to use lower precision operations, and that will save a lot of memories. Also, it will save a lot of computation because to do the matrix multiplications for the lower bits numbers, they are much more faster. So they do this kind of mixed precision training. The weights itself is FP32 higher bits. We convert or custom into lower bits weights and to do forward pass, and we compute the gradient into those lower precision, and we convert them back into 32 FP32 because the original weight we all still want to do updating and in the FP32 precision, and we input to the optimizer, they do the updates. And this kind of idea, simple, and it saves a lot of computation. Maybe half the memory can be saved, and it's 3 times faster for compute. But one problem is that we need to cast this high precision number into some low precision numbers, and those conversions are trying to lose some small valued numbers. For example, this FP16 has lower range, smaller gradient value. For example, some of the lower, if the gradient value is quite small, when they cast them back, some of the value are directly thrown away. They become completely zero. If you have taken any like undergrad, like system classes, this is called an underflow. Like those smaller value are being thrown away because the new range cannot represent those small value. A small fix is that during the spec propagation, those low precision gradient computation, we first scale the gradient up such that it all fits in the range of the low precision representations, and then when we do the gradient calculations, we scale them back to its original values so that we can use the same range of numbers to represent more values we want to represent. And we somehow shift the original gradient into some safer range that our low precision value can represent. So instead of doing those gradient scaling, in fact, we are doing some loss scaling because in the end of the day, we are trying to compute the gradient of the loss with respect to some parameters. If we scale, it's no different that we scale the gradients. For example, this scalar of alpha. It's no difference we scale this gradient or we scale the loss function itself. But doing the scalar scaling, it's much more efficient than scaling all the vector or matrix form of the gradient. So the full pipeline looked like this. We compute the loss. We first multiply the loss by a large scale that we scale the gradient to a larger range. We do the normal back propagation, keep that large, and we downscale the gradient to its original format. And we take a gradient, we take a weight update step, by update the parameters. In this way, we can do this mixed precision training without loss much of the smaller value gradient. The third problem is that every time we want to do larger batch training, like every time people are complaining, I want to do larger batch training to make sure it converges better. The Google needs thousands of the Google Meta needs thousands of GPU, TPU to put not only their model but put a lot of batches of data to make them the optimization much more stabler. So we only have a small GPU. if we put a large batch size within the GPU, it store a lot of activation and samples within the GPU, it will overflow. Like it's simply that the small buckets we have cannot handle so many data we have. The solution is that sometimes we do this gradient accumulations. It is still super simple. We split the large batch data into some virtual micro batches and run them sequentially and accumulate the gradients. Because again, the gradient itself is a linear function. Like you have if I have multiple data run into the models, and the gradient with respect to all the data, because this loss function is a linear summation of all the sample-wise the weights, the loss. So it's nothing but we can take the summation out and just split. For example, we have 512 12 samples. We can divide into some 128 sample batches, virtual batches into the model, compute the gradient for each of the smaller batches, and sum them all together. And then not doing gradients for each micro step, but doing gradients descent for 4 steps. They sum up together, and we can do this gradient accumulation. The only difference is that we would need to scale down the losses a little bit, because later on we want the overall magnitude of the gradient still keep the same. So in the end, we will recap a little bit. So what are we optimize in for the deep learning courses? We want to update 2 things. First is the parameters. We take the input and compute the objective, and we take the gradient of the objective with respect to parameters. It measures how much the total cost is increased or decreased by changing the parameter itself, so that we can change it, so that the loss can change the fastest way. Also, not only the outputs, not only the weights, we can only optimize the take gradient with respect to some of the inputs or features. And at every layer, such kind of output to input or feature gradient can be plays an important part in doing this back propagation, because that's the part they're trying to reuse for those computations. If we take gradient with respect to the input itself, it means how much those input is changes, the output value is increased or decreased by changing the input pixel values. And this idea can be generalized to some examples. For example, we can there was an example called adversarial attack. It means that given an input images, you feed it into a deep neural networks. You take the gradient with respect to the input, such that it maximize certain kind of losses or point out to another classes, and that will give, when they take the gradient with respect to the inputs, it gives you the same shape as the input, and it looks like certain kind of random noises. And you can have the input to go through that direction and feed the new data very similar to the input, but add on a very small noises, and it will give you a completely different output. And that will call an adversarial attack, because it attack model to make a completely different outputs, even if we just give it a small variation. Also, by optimizing input, we can visualize some of the patterns or learned by the network. For example, we can maximize certain kind of neurons. For example, in the deep neural networks, some of the layers, there might be some of the neurons. These neurons might correspond to to some of the concepts, we can optimize. It goes through a lot of layers. We can optimize the input such that these kind of patterns maximize these neurons. And it will give you certain kind of things like this. It will, for example, here we see certain kind of cat-like neurons that we optimize the input to visualize what is learned in this neuron. And in the end of the day, the deep learning is nothing but optimization game. It gives a optimization function, and you go down scales to optimize from initial weights to go to a weight that gives you the lowest cost. The only thing that deep learning is different is that the kind of parameter is parameterized by a deep neural nets, and the objective function is defined by the task. And we will discuss more about how the loss function and the parameter in the next lecture. And again, last time we said that the machine learning is something we want to program your do your programming by learning from the data. And again, we want to bring it up because now we can see that this kind of neural network layer is something programmed by backpropagation. And it's programmed by turning the behavior to match the training examples. And it's programmed by this gradient descent. So now a lot of people are trying to understand the neural network as a circuit of those machine-generated programs and trying to uncover what is the understanding of certain layers by uncovering certain kind of program circuits. And that's a subfield called mechanical interpretability. So next week, we'll cover a lot on the optimizations. That is how we update the weights. Given this gradient, how we actually update the weights. Also, the initializations, the regularization, and the generalization. Like what kind of optimalities is desired by us. And okay, I think that's the end of the second part of the lecture. And we will have another 10-minute break, and we will go through the little bit about the coding session. Maybe it's 30 to maybe we just take maybe 8 minutes. Or otherwise we're late for the course. 8 minutes. Here's that. And if you have any questions, you can still scan the QR code and like put it in the like Slido. So in the last part, I will go through some coding examples for what we just explained above. And this tutorial, Jupyter Notebook already uploaded online. So I will go very quickly. It's best if we can do it within half an hour, so we can dismiss earlier. So once in this coding lab, we'll use PyTorch to inspect into the to see what's happening. We just discussed like the limitation of linear reality, like to show that XOR problem cannot be solved by like linear functions. We'll see how those computational graph go through the chain rows. We'll see the gradient dynamics of using different activation functions or the vanish gradient problem. And we will see some application like fitting and implicit neural representations to the data. And also we will visualize some of the pattern, train a neural network on some of the data and visualize what it learns. But okay, let's try. I'm using the Colab with T5 GPU. One moment. Okay. So first, the first thing we want to discuss is the limitation of the linear model. Like, and in our like discussions, we have seen that okay, it's not linearly separable, but we want to see doing an example to see if it's really the case. For example, we have 4 example 0, 0, 0, 1, 1, 0, 1, 1 with the corresponding output. And we can plot them together, like 2 red dots in the same class, 2 blue dots in the same class. And we can fit a logistic regression model, just the simple linear models. Like we can see, we create a linear regression models, no matter what random seed we chose. I think it can never feed the data well. You can only put the whole space into some subspace. For example, change to another value. It cannot work. You can see that all the 4 dots, they put all 4 dots within one half space. So what we introduced is we create a feature map or create another feature, S1 times X2. And this raise with 1 point up to 1. And by doing that, okay, we have the interaction of 2, the first feature, second feature, the time together, and we put it as a new feature. And we train logistic regression models on the new data. And we can see the decision boundary. Here's the decision boundary that by training the model on the new data, we can see that some of the data are actually like the same category are put in under the same color, and it directly classify the positive data and negative data, even still with linear model or logistic regression models. It's maybe set to reduce the regularization. Yes. So I can change. For example, I can it may use some regularization. I'm not sure how that do. Okay. So that's the case. So we can perfectly classify those XOR data with just a single new feature. Another thing is that we show in the slides, like we want to do those backpropagation efficiently using the chain rules and within a computational graph. And actually, the PyTorch do this automatically for you. They call it autograde. Like the PyTorch build a dynamic computational graph, like as the feed-forward path. So it, even though they didn't show it explicitly, they build a hidden graph, a dynamic graph underlying when you doing your forward pass. And when you're doing your backward pass, it will automatically compute all the gradient on that graph. For example, we have a simple form linear square functions w times x plus b square, and it can break down into a chain of rules. First, a metric multiplication and addition and a square operation. We set those variable in PyTorch, and they will create a node for each of the variables. And you can do it as simple as doing those multiplication, addition, and squares. You will, even they didn't show it explicitly, all those variables will create nodes. These nodes will be computed for their backward pass. Then, so they will create certain kind of value. Maybe I first run it one time. So you will see that for each of those computed variable, they will create a gradient function. I print the gradient function here. The gradient function, the u is the x times w. It will create a gradient function called the power backward function. So these nodes, it will attach to some gradient function. So when we call a backward pass, the backward pass, it will automatically call those gradient functions. The loss has the power gradient function. The v has the add power function, backward functions. The u has the multiplication backward functions. And we can use the loss dot backward to do the auto differentiation. By calling this, all of the nodes preceding it will receive a gradient. For example, here I print the gradient for w. I can also print the gradient of, for example, v. Let's see how that happens. Also, the gradient with respect to wx. By taking this back propagation backward, it will can okay, because this non-time. Okay, because this v variables, it's not an leaf variable that requires grade, so it will not receive a gradient here. I already comment that out. Oh, yeah, that's all. So here we can see that the gradient with respect to x can also be computed. All those, the gradient with respect to x, w, b, they can be computed. But we can do another things. We can set the w to, for example, it's we can set it to not a torch variable, but just a scalar. Let's see how that happens. So we can see that the floating object has no attribute gradient. So every time you want your variable, any variable in PyTorch that receive this gradient, you have to define a tensor that associate to it, so that it knows it need to create a node on the variable so that it can compute the gradient itself. So instead of compute the gradient by the auto differentiations, we can also compute it by hand, because this long chain rule, we can write out the mathematics and do the chain rule, the gradient computation by hand, and it will give us the formulations. And we actually check that it's exactly the same. So the gradient performed by PyTorch auto differentiation is exactly the same as how we compute it by hand. Also, if you do not do the backward function, there will be no gradient here. So quite importantly, you need to take the backward function. So when calling the back function, the PyTorch works backward through the gradient function. Like it goes through the chain rule that we just introduced in class, and it multiply the local gradient at each step, and this exactly what we can we will implement this this backward function in the assignment. The third part is the gradient dynamics. We will see how the gradient value exists in multiple layers of neural networks. Okay. So we define a PyTorch class called deep multi-layer perceptron. We can define, like, for example, how many layers we want. Maybe 20 layers of neural networks, and their linear layer are stacking together, and we have a certain kind of activation function, different activation function. For example, the sigmoid function or the ReLU functions, and we do the here we compute the loss. We do the backward the L2 loss or mean square error loss. We do the loss backwarded, and we would like to check for each parameters, the linear parameter like the W in the model, what is the mean absolute value for the gradient. And we want to plot it out to see that how those gradient magnitude change across layers. So maybe we can add more. For example, leaky ReLU. Leaky ReLU, okay. Leaky ReLU. So we can run this code. Maybe you change the color, maybe black. And maybe blue. We can see that for this, I visualize the y-axis as the log scale. Log scale means that it's very much normalized. Like it's very small here, but this is if I do not visualize in the log scale, the sigmoid function gradient will be quickly diminished to 0. So I visualize in log scales to help us how to visualize their difference. So we can see that for the ReLU and leaky ReLU functions, the gradient magnitude keeps quite steady over time. But for the sigmoid functions, because as we said, its gradient multiplied by the gradient of the next layer. At each layer, the gradient value is less than 0.25. That will gives you very small value when it goes down to the first few layers. And also that's the questions we just answered in class. The first few layers are the one that affect the most. The fourth part is an application of what called implicit neural representation, or a simplest case of what the neural radiance field are implemented. It treats the data as certain kind of functions. It maps the coordinate of inputs to output values. Like, but instead, people are not trying purely using a multi-layer perception to do this. They also add some Fourier features, because maybe I can draw. Because like for 2 points on the same image, 2 very close up points on the single image, when they input to a neural network, the output might be quite similar because their input value x, for example, this x1, x2, y1. This point is x2, y2. Their input value are quite simple. They're quite close to each other. When you put into a linear transformation or multi-layer of linear transformation, their output value will still be quite similar. If you want to present data that with quite quick variability, like certain kind of random noise or human standing here, the edge of the feature, like one point on human faces, another point at the back of the on the background. You'll need that the neural network can learn certain kind of pattern that it will automatically adapt to some high frequency components. That's why people are trying to use some positional information here. Like they use some Fourier features. Fourier features means that you must know some cosine or sine function. When you input it in, it will cause some like high variation functions, periodical functions, or sine functions. Sine function is just nothing but you shifted the cosine function by some thread. So through those input, through those x and y, they will first input to a cosine or sine function with different frequency, and it will give us some features like components, and it will help the model because if the Fourier or the cosine function has very quick variability, even for two features that close up, they will have very different values. So it used the property of those cosine or sine transformations to help the model to learn the variabilities or like high frequency pattern within the neural networks. So here is what we do. First, we need to create an image of a circle in these images. Then we use multi-layer perception. It's input multiple layers. And if we want to use the Fourier features, we first concatenate. We will transform the input into some Fourier sine and cosine domain, like extract some higher dimensional features, and input to the network itself. This gives some high frequency patterns. And here are the results. Like for the network without those Fourier features, the input are purely the index. You will see it shows some blurry pattern because very nearby coordinates, the network will tend to produce very close-up values. But with these Fourier features, it will show sharper edges if there are some sudden changes in the boundary of some objects. Also, you can see that how its loss function are decreases with this Fourier features. Their losses decrease faster, and I think the point is that there is a kind of special multi-layer perception. Input is a coordinate, the output is the value, and you can use that to. Now this MLP store the data itself within the neural network, and you can use the same idea to store nearly all data you have, as long as you can represent as certain kind of coordinate and value problem. The last part is feature visualization. Like once we optimize a network, we want to see what it learns. Like first, we train a convolutional neural network. I didn't mention that before, but in few lectures from now on, we will learn that. We train a convolutional neural network on a small scale hand-digit classification problem, and trying to visualize how the network learns for each of the categories. first, we download the data, we build a simple CNN models, and it has stacking multiple convolutional layers, pooling layers, and so on and so forth. And in the end, it output 10 different categories. I will use like cross entropy to train the models for some iterations, and once it's complete, and we can visualize what it learns for different categories. For example, if I can use the model, the training model, to input some random noises, and we want to maximize the output of for example, the first category, the sixth category, the ninth category, and we minimize the minus value such that we maximize its value. So at this point, we are trying to optimize the input starting from a random noise, such that this kind of input will give us the maximum response for the category. For example, I can give it different numbers they will show us. Like, that's how the pattern model trying to do for the number of 0. Like, it shows certain kind of circle patterns. For example, the another example is this: the model trying to learn the pattern of 5. You will see that, okay, it somehow resembles to a character of 5, and it is the same as for 8. Like, you can roughly see that it's 8. Like, by maximizing the output target of that digit, we optimize not the weights, the input itself. And for multiple steps, for example, here's a 200 step, we can optimize even longer. It should be something else similar, and it will give idea of what the model. If I input this kind of images into the model, it will give a very confident 0 output. So this shows that this model is coming from a random noise, but the model can somehow reverse back the concept of 0 itself. So I think that's the same thing we look at here. If we want to certain kind of neurons, we want to maximize it, it will project back to the input space. It will give you certain kind of, if you are learning in like natural languages, you will give you a face of a cat or a dog or certain kind of eyes. That's in the neural perspective. Here we are trying to optimize for like a category-wise perspective. And I think that's all for the today's coding tutorial. In the last part, I want to take a little bit on the assignment to see what we're trying to do for the assignment. You should be able to see it here. Do you see it in your? So here we are trying to build a neural network from scratch using NumPy. So you cannot use PyTorch or other tools anymore. All you have is I create some classes for you, and it has some class variables like bias, weights and bias, and you need to implement the forward and backward pass of those layers. Also, the activation function, you will need to implement the forward and backward pass for the ReLU function, the tanh function, and the softmax cross entropy losses. Like you have your output of the network, and you have you apply softmax and the cross entropy all together, and it will give you a forward and backward pass. And you put it all together into a multi-layer perception, and you will forward through all the layers, and you will need to train the model will automatically do the step. Like you forward it, you compute the loss function, and you need to implement the backward pass such that you call all the functions within each categories, and you will need to do the simplest form of weight updates and train the models. And I will generate very simple data for you, and you are trying to fit a two-layer network on this data with different activation function. And then in the end of the day, you should be able to see that, okay, your model can do this forward backward pass very easily and can fit the data. So I think that's one particular question I think very useful, because every time I take coding exam, if you are doing a deep learning coding exam, a lot of those exam are based on this kind of question. They want you to handwritten backward propagations, and I think that's even the hardest problem here, because people are trying to call those APIs nowadays, but very few actually know how to write the simplest form of back propagation that we learn in the class. And if you can do this, actually a lot of like deep learning engineer job, you can actually pass the interview. Like I myself has done this by 3 or 4 times. Every time the interviewer says think that they're very, very confident that the interviewees cannot solve the questions. But because I have done if I have done this once in one of the classes, I think it's not super hard. So I think that's the end of today's classes. And please try to finish your assignment on time. And yes, I think that's all for today's classes. We'll just dismiss a few like 10 minutes forehead. So yes, that's it. Thank you.